Okay, I started to answer the question there, but it took me away from where I wanted to go. I didn't have room to do it, so I draw this horrible looking circle here. Yeah, but don't pay any attention to that. Okay, so what we have is the voltage of the source is then I max times all this stuff. Okay? Well, I combine these and I can add these if I know what the cosine of omega t minus pi over 2 is in terms of sines and cosines, right? Of pi over 2 and omega t. I can easily combine these into some multiple of the cosine of omega t plus phi, where phi depends on the relative magnitude of r and 1 over omega c. Okay? And I'm using x somewhat inappropriately, but we'll straighten that out, for the quantity here. Okay, it's not a resistance, it's a combination of this resistance and whatever 1 over omega c is. But 1 over omega c kind of acts like a resistance. Okay? Because the bigger 1 over omega c is, the bigger this x is going to be. Of course, the bigger 1 over omega c is, the closer the resultant on your phase diagram is going to be to the direction of the capacitor voltage. Okay, well, we'll worry about that later. Just simply, we do a little bit of algebra, we can put these, a little bit of trick, we put these together, we can get something like this. This acts like a resistance, something analogous to resistance, but it's out of phase with this resistance, okay? It's out of phase by 90 degrees. Okay? So we call this 1 over omega c, we use the term x sub c. So it's sort of like resistance, we call it a reactance, specifically capacitive reactance. And we've seen how this works in class, in lab. Okay, what happens if you crank the capacitor forward for a while, then reverse it for a while? Okay? Well, what happens is the capacitor builds charge, which reduces current. Okay? Well, it's a current reducing thing, like, and that's what a resistance is too, is a current reducing thing. Okay? The faster you crank it, the less effect you have because you're not building up any charge. Okay, the capacitor we have, you got to crank it for a few seconds to cut the charge in half, right? Or cut the current in half, and vice versa. Okay? If you crank it every 1/10 of a second, the capacitor is never going to have time to build much of a charge. Now, if you have a capacitor you use in most real applications, then the capacitance is much smaller than the capacitance we have, right? But if you crank it much faster, then let's say the half-life of the capacitor, the time it takes the capacitor to build half its charge, the faster you crank it, the faster you switch the current, the less effect you're going to have on the current. More slowly, the more charge builds in the capacitor, and the more charge is in the capacitor, the more you resist, or the more the EMF on the capacitor fights the EMF of your source. And if you don't believe it, grab one of the interfaces in the generator and the capacitor and play around with it. You'll see that. So you want that to be something you really understand, because this circuitry is extraordinarily important. Okay? So 1 over omega c, well, this means when c gets small and omega gets big, this gets really small, which means that this gets really big, right? Small capacitance, fast omega. Large omega. Yeah. Great. A lot of frequency. So this is really big. Well, it's, okay. A large combination of omega c, which could be really fast omega or really small c, okay? Or really big C, I'm sorry. Gives us a small result here. Okay? Really slow omega, really big C gives us a big result here, which is totally consistent with what I just said, but probably not what I said 2 sentences ago. Okay? So this is capacitive reactance. When omega C is big, you're not having much effect. Capacitor's not having much effect in the circuit. When omega C is small, it's having a big effect. Okay? So that's reactance. In other words, when omega C is big, you're not interfering much with what this voltage does across the resistor. Okay? Okay, well, now there's another thing, and that is when you have an inductor. Now, you accept that if you're changing the voltage, if the voltage reverses very quickly, the capacitor doesn't have time to build up a charge. Okay? 1 over omega C is small because omega's big. Okay? But what's happening if you got an inductor in the circuit? Well, you're trying to change the current. You're trying to reverse the current fast. Right? If you're trying to reverse the current fast, what's going to happen?
The inductor is going to resist it?
Yeah, you're going to get a back EMF from the inductor that just shuts everything down. Okay? So another factor is inductive reactance. That's XL equals omega L. Bigger inductor, more back EMF. Bigger omega, more back EMF. So this acts like a resistance that suppresses your current, given your voltage. Okay? Make sense? Now you notice, and that also gives you, okay, well, you end up, and I could do the calculus, it's every bit as simple. You just take the derivative of the current, and you get the rate of change of the current, and you're going to get a negative sine of omega, a negative omega sine omega t, right? I mean, that's straightforward. You take that derivative, and that shows you that di dt is 90 degrees ahead of the voltage, of the current. Okay? And you end up with a picture that looks kind of like this. There's your maximum voltage across the resistor. 90 degrees this way is your maximum voltage across the capacitor. 90 degrees this way is your maximum voltage across the inductor. And these things rotate around a circle. They have a vector sum. Okay? Now, the way I've drawn this is bigger than this, right? What's this do? This gives you a resultant that's back this way. From your V sub r. Now I'm going to try to draw a circle. Wish me luck. No worse than usual. Okay? So this picture tells me how far out of phase I am with this one. Okay? That makes sense? Just by analogy with the other one, we'll do more with it, but I want you to actually play around with it a little bit. Okay? if you have no resistance, then you have just these two, which have a resultant that looks like this. Okay? And what's going to happen to these voltages? As this thing goes around, this voltage is going to be at a maximum when this one's at a minimum, right? Okay? Well, actually I'm not, that's all I'm going to say about it right now, because we want to actually get our hands on the equation and see how this works out. But I would just want to give you the idea of the phasor, which you can now read about in your book. Because you know everything if you understand what I said, and if you don't, read your book and see. Okay? This is one of the things that people find really hard to understand, but I don't think if you understand what we just did or think through it, you're going to have that much trouble with it, because of the way we build it up in lab and so forth. I'm probably wrong. I'm probably going to be depressed because you don't understand it. And you don't want me to be depressed, because then I grade you harder, right? So understand it. Okay, well, you get the idea.